Welcome to Chapter 4 of Class 8 Science, Electricity, Magnetic and Heating Effects. In this exciting chapter, we'll explore the fascinating connection between electricity and magnetism, discover how electric current can generate heat, and learn about different types of batteries. We begin with a story about a science exhibition where students are amazed by a lifting electromagnet, an iron nail that becomes magnetic when connected to a battery. This demonstrates the magnetic effect of electric current, which was discovered by Hans Christian Oersted in 1820. We'll recreate his famous experiment, build our own electromagnets, investigate the heating effect of current, and explore how batteries work. Get ready for some shocking discoveries. Let's begin with the magnetic effect of electric current. In 1820, Danish scientist Hans Christian Oersted made a groundbreaking discovery during a classroom demonstration. He noticed that a compass needle deflected whenever he closed or opened an electrical circuit nearby. This was revolutionary because it revealed a fundamental connection between electricity and magnetism that nobody had recognized before. In Activity 4.1, we'll recreate Oersted's experiment. We'll set up a simple circuit with a switch and place a magnetic compass near the wire. When we close the switch and allow current to flow, the compass needle deflects. When we open the switch, the needle returns to its original position. This proves that an electric current produces a magnetic field around the conductor. The region where this magnetic effect can be felt is called a magnetic field. This discovery opened up entirely new possibilities for using electricity. Now let's explore electromagnets, temporary magnets created by electricity. An electromagnet consists of a coil of wire wrapped around an iron core. When electric current flows through the coil, it becomes magnetic. When the current stops, it loses its magnetism. In Activity 4.2, we'll build a simple electromagnet using an iron nail, insulated wire, and a battery. We'll wrap the wire tightly around the nail to form a coil, connect it to the battery, and test if it can pick up paper clips. We'll discover that the nail only attracts clips when current is flowing. In Activity 4.3, we'll investigate further by making a cylindrical coil and testing it with and without an iron core. We'll find that the coil with an iron core becomes a much stronger magnet. Electromagnets have two poles just like permanent magnets, and we can reverse the poles by changing the direction of current flow. The strength of an electromagnet can be increased by using more cells or more coil turns. Let's explore real-world applications of electromagnets, particularly lifting electromagnets. These are strong electromagnets hung from cranes in factories and scrap yards. The crane operator can control them by simply switching the current on and off. When current flows, the electromagnet lifts heavy iron and steel objects. When the current is switched off, the magnetic field disappears, and the objects are released. This makes moving and sorting metal items much more efficient than mechanical methods. The strength of an electromagnet depends on several factors: the amount of electric current, the number of turns in the coil, and whether there's an iron core. More current or more coil turns makes a stronger magnet. Interestingly, the same principle works on a planetary scale. Earth itself behaves like a giant magnet because of electric currents generated by the movement of liquid iron in its core. This magnetic field helps migratory animals navigate and protects Earth from harmful space radiation. Now let's investigate the heating effect of electric current. When electric current flows through a conductor, the moving electrons collide with atoms in the material, generating heat. This is why wires get warm when current flows through them. In Activity 4.5, we'll use a special wire called nichrome wire to observe this heating effect safely. We'll set up a circuit with the nichrome wire and notice that it gets warm when current flows. We must be careful not to touch the wire for extended periods to avoid burns. The amount of heat generated depends on several factors: the magnitude of the current, the material of the wire, its thickness and length, and how long the current flows. When we repeat the experiment with 2 cells instead of 1, we'll notice more heat generated due to the higher current. This heating effect is useful in many household appliances like electric heaters, irons, kettles, and hair dryers, but it can also cause problems like energy loss and fire hazards if not properly managed. Let's explore how batteries generate electricity. Batteries convert chemical energy into electrical energy through chemical reactions. We'll start with voltaic cells, one of the earliest types of electric cells. A voltaic cell has 2 metal plates made of different materials, called electrodes, dipped in a liquid electrolyte. The chemical reaction between the electrodes and electrolyte produces electricity. When the circuit is connected, current flows from the positive terminal to the negative terminal. Over time, the chemicals get used up, and the cell stops working. We say it's dead. In Activity 4.6, we'll make our own voltaic cell using lemons. We'll insert copper wires and iron nails into lemons and connect them in series. The lemon juice acts as the electrolyte. We'll connect an LED and see if it glows, proving that our homemade cell is producing electricity. Different metal pairs work as electrodes, with some metals naturally acting as positive electrodes and others as negative electrodes due to their chemical properties. Now let's examine dry cells and rechargeable batteries, which are more practical for everyday use. Dry cells are called dry because they use a paste-like electrolyte instead of liquid. They have a zinc container that acts as the negative terminal and a carbon rod with a metal cap as the positive terminal. Dry cells are single-use. Once they're used up, they must be disposed of. Rechargeable batteries, on the other hand, can be recharged and reused multiple times. This reduces waste and saves money. There are many types of rechargeable batteries used for different applications, from small batteries in watches and phones to large batteries in electric vehicles. However, even rechargeable batteries don't last forever. They slowly wear out after many charge cycles. The most common type today is the lithium-ion battery, found in most portable electronic devices. Scientists are now working on solid-state batteries that use solid electrolytes instead of liquids or pastes, which would be safer, charge faster, and last longer. As we conclude this chapter, let's review the key concepts and their real-world applications. We've learned about the magnetic effect of electric current, how current flowing through a conductor produces a magnetic field. This principle is used in electromagnets, which are temporary magnets that can be turned on and off. We've explored the heating effect of current, how conductors heat up when current flows through them, which is utilized in various heating appliances but also requires safety precautions. We've examined how batteries work by converting chemical energy to electrical energy, and we've distinguished between different types of batteries including voltaic cells, dry cells, and rechargeable batteries. These principles have wide-ranging applications from household appliances to industrial machinery. Safety is crucial when working with electricity. We must use appropriate materials, prevent overheating, and dispose of batteries properly. The connection between electricity and magnetism powers much of our modern world, and understanding these principles helps us use electrical devices safely and efficiently.